Hello everyone, I'm Sifan Tang from the University of Utah. Today, it's my pleasure to talk about OpenFPGA towards automated prototyping for versatile FPGA architectures. Let me quickly introduce how popular FPGA is nowadays. Basically, you can see FPGA is everywhere in the modern computing architectures and systems due to their unique advantages. For example, FPGAs are extremely popular in wired and wireless communication systems, where people exploit the mission reconfigurability of FPGA chips to implement different communication protocols so that people can easily upgrade communication protocols when a new standard is coming. A second application, as you see, as you may be very familiar with these days, is the data center, where FPGA is used as a coprocessor sitting aside the CPU unit, working as a signal processing, AI inference, and other acceleration functionalities. Also, FPGA is very popular in defense applications, where the FPGA can serve as a secure media with designed bitstream in a secure format, so that any attackers cannot get any internal functionality of a SoC used in defense applications. Then why you need OpenFPGA, since there are already a lot of FPGAs on the market? Because we want to automate the process of prototyping customizable FPGAs. Imagine, in a traditional way, to prototype an FPGA architecture to the chip, you need to hire a number of senior architects, as well as a big group of hardware and software engineers. And hopefully, within such large manual effort, you can get a production-ready layout in 1 year. In addition, you also have to spend a lot of human effort in developing the associated CAD tools. However, OpenFPGA makes this life much easier. Ideally, you just need one architect, and then use OpenFPGA. We can automatically generate production-ready layout in 24 hours. You don't need any additional effort to build your CAD tools because it is already to be used. As a result, we can expect a very short time to market using OpenFPGA to prototype your chips, as well as a significant reduction in the manual effort required. Let me give more in-depth introduction on the OpenFPGA framework. Nowadays, OpenFPGA is a fully modularized code base where integrate various tools from collaborators. As you can see in this figure, we have integrated a lot of third-party tools in our design flow, which are in the gray box. We aim to reuse the popular VTR architecture file from the #1 FPGA architecture exploration tool in academia, so that users can easily port their architecture exploration results to OpenFPGA for prototyping the FPGA architecture. The OpenFPGA framework can be used for two design purposes. The first one is the chip design flow, where you can describe your FPGA architecture in the XML description, and then we can generate the Verilog netlists, and you can use the backend tools to convert the Verilog netlists into GDS2, and send it to Foundry and tape out the FPGA. The second design flow is so-called end users flow. This is after you have your FPGA chip returned. OpenFPGA has an internal bitstream generator auto-tuned for your architecture. You don't need to develop your own tools again. As a result, OpenFPGA complies with many standard file formats, along with the modularized code base. It's a very modern software platform. You can easily use third-party tools, which is using the standard formats. In terms of support on the third-party tools, as I stated in the previous slide, we can support a lot of them. For example, here in the backend tools, we can support the most popular commercial tool suites like Synopsys ICC Compiler 2 and the Cadence Innovus. For STA, we also covered the Synopsys Primetime and Cadence Temperos. In terms of verification, we support most popular commercial HDR simulators from Synopsys, Mental Graphics, Cadence, as well as open source Icarus iVerilog tools. OpenFPGA also supports to run formal verification for your FPGA fabric. And OpenFPGA has also been tested on a wide range of PDKs, including the academia ASAP 7nm, as well as commercial PDKs, EDEST, Global Foundries, TSMCs, especially the recently open-sourced Skywater 130nm PDK. OpenFPGA offers full customizable FPGA architecture modeling. We allow chip designers to customize any circuit element at any location of the FPGA fabric. For example, we display the FPGA architecture on the left side of this slide. You can see it's a very modern FPGA architecture we can support. I would like to highlight you can really define a circuit element, for example, a multiplexer in one level structure in the logic element, and also you can define a different routine multiplexer circuit implementation, EDEST, a two-level multiplexer for a connection block. Based on that, you can also exploit different cell implementation to trade off power, area, and performance. For example, you can define high-speed flip-flop in the data path. And you can define a low-power flip-flop to be used in the configurable memory. Beyond the circuit element, we can support various configuration protocols. You can also customize it and then use it in your own way. Beyond that, how do we support FPGA architecture? Basically, we support any architecture that can be modeled and supported by VPR framework. In particular, we can support very flexible, programmable logic block architecture. Take the example here. In the programmable logic block, we allow users to define for example, a single mode logic element, as well as more than multi-mode logic element, capturing the most advanced logic element design in Xilinx and Intel, these cutting-edge FPGA devices. We offer versatile configuration protocol. I show a very quick example here. We can support configuration chain across the fabric, like you see in the left corner. Also, we support multiple regions for your configuration chain. You can define multiple heads for your configuration chain to speed up your configuration time for FPGA. So we offer XML-based architecture descriptive language to model the FPGA architecture as well as the circuit designs. For example, users can define a circuit modular in XML, and OpenFPGA can auto-generate to Verilog netlists. Also, we support that users can define a circuit modular referring to a standard cell or a customized cell. Then OpenFPGA can automatically bind this circuit model to a cell without auto-generating the Verilog netlists. As we said about the supported circuit designs in previous slides, I want to clarify and highlight what do we support in detail. Our architecture description language aims to capture state-of-art design topologies. Nowadays, you can see in FPGAs and ASICs. The full details you can find in the link below, but I would like to highlight a few critical components you may see in the FPGA architecture. For example, the look table. We support any input size for look table, as well as single output and flexible look table architecture. Regarding to the routing multiplexers, we support any input size of routing multiplexers, as well as flexible structure for the multiplexings. For example, one level, multi-level, and tree-like, as well as standard cell multiplexers, which each of them offer a different level of power, performance, area trade-offs. This really unlocks the customizability of FPGA prototyping for different performance requirements. Moreover, we also support very flexible definition for hard IPs. For example, you may have a block RAM IP, adder IP, and multiplier IP to be integrated in your FPGA architecture, and we support all of them. Let me look into the tools integrated in OpenFPGA framework. For example, the FPGA-Verilog is designed to output fabric netlists. FPGA-Verilog can output two types of netlists. One is so-called synthesizable netlists, where FPGA-Verilog output a behavior description for the full FPGA fabric, and you can call standard ASIC design flow. For example, you can use design compiler to synthesize the Verilog, and then use IC compiler 2 to generate design GDS2. Alternatively, OpenFPGA also supports the generation of technology-mapped netlists. As we stated, our XML language supports the binding to standard and custom cell library, so that you define this, and OpenFPGA can output technology-mapped Verilog netlists using the standard and custom cells you defined. And these netlists can be directly used in IC compiler 2 to generate GDS2 netlists. Another functionality of FPGA-Verilog is the Testbench generation. Verification for FPGA can be very cumbersome, but we offer auto-generation for these testbenches. In particular, we support two types of testbenches. The first one is the full testbench. It's a self-testing testbench designed to test a complete FPGA run in practice. It means it will simulate the whole process where you download your bitstream to the FPGA fabric and you start the operating phase. We offer output checker so that this is self-testing, feature-enabled. The testbench will compare the output of the FPGA fabric to the user's implementation and make sure that your functionality are equivalent. FPGA-Verilog can also output a pre-configured testbench, because in practice, we notice that full testbench could be very time-consuming. To accelerate some verification, the verification process, we designed this pre-configured testbench. You can see we propose a pre-configured FPGA modular where we encapsulate the FPGA fabric with configured bitstream. into the same port mapping as users implementation Verilog in Verilog format, so that people can use this pre-configured FPGA Verilog in the post-OpenFPGA verification without creating additional test benches. For example, in the pre-OpenFPGA verification, users may craft their own Verilog test bench, which represents a high coverage for testing. You don't need to modify a test bench. You can directly reuse it to verify the FPGA fabric, which is mapped, and make sure they are equivalent, and tested under the high coverage testing vectors. Another one is the formal compatibility. As I said, the pre-configured FPGA modular share the same port mapping as the user's Verilog netlists. Then you can use the Verilog netlists, users' Verilog netlists, as a reference. Send both of them to Formality or for any other formal tools to perform 100% coverage on a functional equivalence. FPGA Bitstream is another tool integrated into OpenFPGA framework, which aims to offer open source Verilog-to Bitstream conversion for end users. So this one offers non-recurring engineering on the EDA toolchains for any FPGA you can model in OpenFPGA framework. So it means once the architecture is done, the EDA toolchain is ready to use. We also offer many reference methodologies which are auto-tuned for FPGA fabrics. So we can make sure that the FPGA toolchain is auto-tuned for your customized FPGA fabric. More importantly, thanks to the open source nature, users can continuously benefit from the quality of result improvement from the open source community support. Last but not least, OpenFPGA also integrates an SDC generator we call FPGA SDC, which can output and outgenerate timing constraints to cover the full FPGA fabric. In particular, we allow users to define their timing constraints in the VPR architecture description file. Take the example here. We can constrain the timing from any input of log table 6, a 6-input log table, to the output of this log table. FPGA SDC will take this timing definition in the architecture file, convert it to standard SDC format. Then you can use these timing constraints for your backend tools as well as during the sign-off. Which means using OpenFPGA framework, you can close the loop of a timing constraint backend flow with respect to performance requirements from users' implementations. For example, you may have a few benchmarks, and you want your FPGA to operate at a given speed for each benchmarks. Therefore, you carefully craft your architecture with timing requirements. Then you can use OpenFPGA to auto-generate SDC and constrain your backend tools, and automatically sign off your FPGA fabric to see if the timing constraints are correctly met or not. If not met, you just need to modify your FPGA architecture definition and then rerun the flow until all your timing constraints are met. Let me talk about two showcases for OpenFPGA. The first one is an embedded FPGA fabric, which is built using the TSMC 14nm technology. The tool set we're using to generate the layout is the Cadence Innovus. The total layout area is 7 mm square. The whole runtime of layout generation is 24 hours. In particular, I would like to emphasize we use custom cells to build high-performance routine multiplexers. When compared to previous work, we can see by only using 2 custom cells, the FPGA-Verilog will generate is 1.8 times smaller in area than the previous art. The second showcase is a heterogeneous FPGA built by Global Foundry 12 nm PDK, as well as Synopsys IC Compiler 2. The total layout area is 9 mm square, and the runtime of the whole flow is 12 hours. I would like to highlight this FPGA is built purely with standard cells. It means you can instantly benefit like 3 times delay improvement in this case when porting from a technology node to a more advanced technology node with very few manual efforts on your FPGA architecture tuning. Let me summarize OpenFPGA framework for you. It's a framework for Android hardware development for customizable FPGA fabrics. We offer auto-tuned and open source tooling for any FPGA architecture we can support. Thank you for your attention. Please feel free to try OpenFPGA and bug us.